fiber optic cable industry for nearly 28 years, and I welcome the opportunity like this to share what I've learned over the years with everyone. And without further ado, let's get going. So today's class is not only a continuing member of the series of classes that we're doing to help everybody learn more about fiber optic cable and fiber optics in general, and to share information. It's also an opportunity if you need professional development hours to get some professional development hours, continuing education credit. So we are registered with RCEP and we comply with their requirements, and this is a statement to that effect. This does not mean that they endorse anything that I say here. It just means that our format is consistent with their program. This course, the purpose statement is to talk about the basics of ADSS cable design. So let's go ahead and move on. Specifically, we're going to learn about the 7 design elements of ADSS. You'll see them listed here. We will talk about each one. We will also discuss how the tubes and the optical core should be made and why this how is very important to long-term performance. We're also going to do a primer on how you do sag and tension calculations or get the sag and tension data that you need. And we're also going to tell you how to determine when you need a track-resistant jacket. And here are the ground rules. So we've already done the introduction and sound check. The presentation itself should last about 75 minutes. So back to continuing education credits, that's 1.25 credit hours. You can use chat for questions during the presentation. I'm assisted today by my colleague Dan Berg and my other colleague Justin Fry, and they'll be screening questions during the presentation, so that is okay. However, I won't actually see the chats, so they'll handle what I call the simple questions, and if something needs to be held to the end, they'll let you know. And at the end, we will have a question and answer session with me, 10 to 15 minutes or however long it goes. And we do ask, though, that there's no business during that. So like if you've got a project going on with NCAB, now's not the time and place to talk about the issue that you have with your order with NCAB. So we just want to talk about the technical questions related to ADSS cable design. So I think everybody will understand that. So let's get going. So first, we're going to review just a couple basics about optical fiber and loose tubes, because the principles behind these apply whether we're talking about ADSS cable or optical ground wire or any other type of fiber optic cable. So to begin with, the fiber itself. Now I'm only going to hit the highlights on fiber, and you see on here one topic is circled, and that's that the most common, overwhelmingly common type of fiber that we use is so-called low water peak single mode fiber. So when people talk about single mode fiber, they're generally talking about what's known as the low water peak single mode type fiber. The current standard for that is ITU-T G652D. That's an international standard recognized by everybody. An example of this type of fiber is Corning's SMF28 fiber of families. We currently use SMF28 Ultra. That's our standard for low water peak single mode fiber. But there are lots of other examples of it. OFS has their all-wave series of fibers, and there are other companies, other world-class companies out there with their basic, plain, vanilla, whatever term you want to use, single mode fiber. And an important point about those different fiber suppliers and their fiber is that those products are splice compatible. So if you've bought cable from in-cab using Corning fiber, you can splice that to some existing cable that you have from another supplier that maybe used a different supplier's single mode fiber. And you can go up to about 60, 90 miles with today's low water peak single mode fiber. Other types of fiber, just the only hit in passing, is the non-zero dispersion shifted fiber. The two most commonly used NZDS fibers are Corning's Leaf and OFS's True Wave fiber. Those are generally not splice compatible in the field. And we do, with ADSS, we do a little bit of multimode cable from time to time. You've got two flavors of multimode, 50 micron or 62.5. 62.5 was very commonly used in the United States, but not so much else outside of the United States for a long time. 50 micron was more widely used outside of the United States, and these days we're starting to see more 50 micron fiber used in the United States when it's used. But in our plant, 99% of the fiber that we use is the low water peak single mode fiber. The performance specifications for fiber, the most important one there is attenuation. And attenuation is the loss of power over distance. It's expressed in terms of dB of power lost per unit length. Most commonly is dB per kilometer, but you could do it dB per mile or dB per furlong if you wanted to. And what that means is basically that you inject a certain amount of power, say 10 dB at the input, and 10 miles down the road, you have less than 10 dB. Maybe it's 9 dB, maybe it's 8 dB. It depends on how much loss you had in the cable, plus your splices and connectors on that optical link. Chromatic dispersion becomes important if bandwidths are very high, like you're using dense wavelength division multiplexing, or if you're going very long distances. With ADSS, we don't see that too much. So again, the most important specification is the attenuation. So moving from the fibers onto the tubes, these days in outdoor cables, and specifically in aerial cables such as ADSS, the overwhelming majority of cable, again, like on the order of 99%, has loose tube construction. And loose tube is in contrast to a competing technology in the early days called tight buffer. But tight buffer has found it's more applicable in indoor cable applications. So outdoor cables, you generally see loose tube. An exception might be with ribbon cables, but that's another topic for another day. The loose tube design concept became popular for outdoor cables, and in particular aerial cables, because the loose tubes allow the fibers to move in response to changes in elongation. So what you do is you lay the fibers in a tube in a nice sinusoidal shape, as you see in this picture. And when that tube is stretched by like a change in tension on an ADSS cable, or in say an optical ground wire, an OPGW cable, it could also be changes in temperature. Changes in temperature don't come into play with ADSS, but changes in tension are definitely in play with ADSS. Either way, when the tube begins to be elongated, the fibers aren't really seeing that tension. They're just sort of flattening out. They're straightening out in response to the change in length of the tube. And what that means is that you're protecting the fibers from the tension that's on the tube. An important concept that comes from this is what's known as zero fiber strain margin. And so that's the point when the fibers begin to experience strain. And it's for a cable, it's expressed in percent rated breaking strength commonly. Other ways you could do it, but commonly. In general, more is better. In addition to what you can get in the tube itself, if you strand a tube like you see in this picture down here, you further increase the excess fiber length, which is the extra fiber per unit length of tube or cable. Again, in general, higher is better. So if I strand the tube, I get a similar effect that when the cable is beginning to stretch, at first the tube is trying to straighten out, but it can only go so far before the fibers are pulled into the center and everything sort of locks down, and then the tube begins to stretch and you get the effect that you see here at the top of the slide. So remember these concepts, zero fiber strain margin and excess fiber length, they'll come into play later in the presentation. So ADSS cable, I want to begin by reviewing a couple of the obvious things there too. ADSS stands for all dielectric self-supporting, and the dielectric means no metal parts. And it's one of my pet peeves in life that people will often refer to any kind of a cable with a plastic jacket as an ADSS cable, and that's not true. An armored cable, for example, that goes underground and has corrugated steel in it is not really dielectric anymore. It's an armored underground cable. Plus, it's not self-supporting. And the self-supporting part means that an ADSS cable is designed to support its own weight. So a plain duct cable is not an ADSS cable, it's a duct cable. It does turn out, though, that in any place you can use a duct cable, you can also use an ADSS cable. It might be a little bit overkill, but you can do it. But the reverse is not true. And that's why the language, in my opinion, is important. You can't take a duct cable and hang it in the air because it's not designed to support its own weight. It'll just break. So again, the key takeaways, it's dielectric, no metal in it, and it's self-supporting. It's designed to support its own weight. The standards here in the United States are the IEEE 1222 standard, and internationally there's IEC, I've left out the IEC there, but IEC 6074-4-20. That's a mouthful. You'll also hear ADSS talked about as short span ADSS and medium span ADSS and long span ADSS, and what does that really mean? Hold that thought later for when we get to talking about sag and tension. Now, I mentioned at the beginning that we're going to talk about the 7 design aspects of ADSS. And it might seem to you that there are just too many choices. Get the pun there? Because most of the time there's a choice between this and that. Sometimes there may be a third or more option in there. If it seems like this might be confusing, don't worry about it. We're going to break these down and help you understand what each choice is, and then you can make informed choices. Let's begin. The first of the 7 is jacket configuration, and the choice that you have is double jacket versus single jacket. So here's a sketch, a cross-sectional view of a double jacket ADSS. So you have the optical core in the center, so plastic tubes stranded around some kind of a center element, and then an inner jacket protecting the optical core, then your strength member. This one, as shown, is ARAMID, and then an outer jacket. In a single jacket design, you omit the inner jacket, so you get the same optical core, but then directly over it is applied your strength members, and then on top of that, you've got the outer jacket. It turns out in this case that there are trade-offs between the 2 design concepts. Double jackets is a more traditional design, one of the earliest designs that came out. And its advantage is it has the highest reliability. That inner jacket does protect your optical core, and that's a good thing. It's also good for long spans, so you can easily do over 1,600 feet. But it does have some disadvantages. First of all, it's more expensive. Depending upon the fiber count, it might only be 5%, but it could easily be 25%. And just as importantly, you're increasing the diameter and weight of the cable, on the order of 10 to 20%. Single jacket designs is a newer design concept, but when I say newer, that's kind of a relative thing. It has been around for over 20 years. The advantages it offers are that you're reducing cable diameter and weight, and you're reducing cost. Those are good things. But the disadvantages are lower reliability because you've omitted that inner jacket, and you also limit your span lengths. So in general, I think you need to keep it less than 650 feet if you're using a single jacket design. So we've talked about what they are. What choice should you make? Double jacket design you should use if any of the following applies. So if your spans are more than 600 feet, I recommend a double jacket design. I know a single jacket could maybe do 650, but I prefer to have a little bit of a margin for error. If your fiber count goes above 144, again, I definitely think you need to go to a double jacket design. And if you're concerned about long-term reliability, it's a absolute must stay in service cable, then I think the double jacket design is the right choice. Single jacket design, as long as all of the following apply, then I think it's a good choice. If the spans are less than 600 feet, if your fiber count is 144 or lower, and if good reliability is good enough, it's a fine choice. So on this particular design aspect, the optimal choice depends upon your project details, what you're trying to do. Next up, jacket material. You got two choices and not really a third. The two choices are high density polyethylene, HDPE, and its advantages are it's tough and durable, but the disadvantages are it's susceptible to cracking, especially at low temperatures. It does make splice prep harder. It makes it significantly harder to get into the cable, and it is more expensive. Medium density cable, and by the way, I should mention, outwardly, you would not be able to tell the difference between these two or even the sort of third I talked about. They just look like black plastic. But the density is the key to what's going on there. High density just means that there's actually a lot more material crammed into the same space than, say, medium or low. Anyway, back to medium density. It's still tough and durable, and it's easier to remove during splice prep relative to high density polyethylene, and you save a little bit of money. But the disadvantages is it's arguably not as tough and durable as HDPE is. And then the third sort of choice you have is low density polyethylene. And by the time you're at low density polyethylene, the material is noticeably softer. I mean, you can feel it with your fingers. Can't see it so much, but by the time you're touching and handling it, you can feel the difference. And we think that that's well suited for an inner jacket only. So what choice do you make? Our opinion, medium density is the best overall choice because it balances the toughness and durability with the cost and ease of splice prep. Low density polyethylene, though, we think is a great choice for an inner jacket, and because that facilitates completing the splice prep process. So next up, what strength material do you use? Now, most people in the United States are only familiar with ARAMID, which is more commonly known, or perhaps at least as commonly known, as KEVLAR. KEVLAR is just the specific trade name of DuPont, who invented this material. but the generic name for it is ARAMID. So, Kleenex officially is a brand name too. The generic thing would be facial tissue. It's that kind of situation. It's the original and most used strength material. So in the United States, it's probably like 99% of ADSS and duct cables use KEVLAR. Or, excuse me, now I'm doing it, ARAMID. Outside the United States, though, you find the use of fiberglass, which we'll talk about in a minute, but you don't see fiberglass a whole lot in the United States, and you'll see why in a minute. So ARAMID has very high strength to weight ratio. It's on that basis, strength to weight, it's 5 times stronger than steel. It's highly thermal stable, and it's so stable, it's way above and below the range of temperatures that you would use an ADSS in. It becomes easy to limit the fiber strain. Remember, we talked about that before. We talked about it more as tension on the fiber, but the same thing. So you can limit the tension that the fiber experiences at the maximum rated design tension of a cable. We'll talk about that later, what this means, to not more than 0.2%. And that's, we consider the ideal limit. 0.2% is a limit that Corning put out in a paper they published in the early 1990s. And the short summary of that paper was that if you're going to allow strain on fiber, it was good to limit it to 0.2% or less. And that gave you a low, but not a zero probability of a fiber failure expressed as number of fiber breaks per fiber kilometer per year. That number ended up being really low. And so this is still a benchmark used by cable manufacturers around the world. But the disadvantages of ARAMID are that it is more expensive than fiberglass, and it can become conductive in water. So if you have a jacket breach and water gets in and the KEVLAR, now I'm doing it again, the ARAMID gets wet and you have a high electric field, you can have bad things happen. Fiberglass yarn is less expensive, significantly less expensive than ARAMID. And its big advantage, though, is that rodents, which for an ADSS cable includes squirrels, they don't like to chew on it. So if you used a cable, an ADSS cable, where its strength is coming from fiberglass yarn, you automatically can get a rating of a C on rodent resistance. An ARAMID cable gets an F. The ARAMID, the rodents and squirrels just chew through it, no problem. Maybe it's even tasty to them. I don't know. But in any case, with fiberglass, without doing anything, you can get a C, A, B, C, D kind of rating. But the disadvantages are it's much less mechanically efficient compared to ARAMID. And it doesn't have quite the thermal stability either compared to ARAMID. And consequently, you end up having to give up a little bit of fiber strain. Remember, I said you would like to keep it below 0.2%, but with the fiberglass ADSS, you might have to allow it to float up to 0.3 or 0.4%. And we'll come back and give you some context for that later. Your third choice for strength material is relatively new, and that's using fiberglass reinforced plastic rods, which almost looks like an armoring on the cable. The advantage to this construction is that rodents, again including squirrels, don't like to chew on it. You just using fiberglass rods gets you an A rating. It also gives you very high crush resistance. And because of that, it means that you can take a cable like this and direct bury it underground as well. So you've got a cable that's very versatile. We also think that it's shotgun resistant, and we're doing some testing on that to confirm if that's true. So at the moment, that's just a hypothesis. We're going to find out if that's true or not. But it has some significant disadvantages. The disadvantages are that it's expensive. It greatly increases the diameter and weight of a cable, and you have to have an inner jacket when you're working with the fiberglass reinforced plastic rods. These facts mean that you shorten your available span lengths, and I say maybe harder to splice prep. It's different to the splice techs. I don't think it's really more difficult than what they're used to working with, but it's definitely different. And so the perception of it being harder is going to be there because you do have to remove these rods during that process. And I just wanted to comment, why is this important? Well, because the UTC did a survey of utilities in the United States, and the #1 field problem with ADSS has been shotgun damage. That's why we're doing some testing to find out if this is really a benefit for giving shotgun resistance to the cable or not. But the close #2 problem was rodent damage, in particular from squirrels. And here's some pictures. I love this picture of this squirrel. I just wonder what the heck he was thinking about. But here and here you see some damage where rodents, and again, probably squirrels, especially this one, were chewing on a cable. They have no problems chewing on ARAMID at all. And here you see where a shotgun has damaged a cable. So if you have 3 choices for strength material, ARAMID, fiberglass, and FRP rod, fiberglass reinforced plastic rod, what should you make? What choice should you make? And we think that again, the optimal choice depends upon what you're doing. There's not really a bad choice here. It just depends upon what you're doing. Your default choice should be ARAMID, unless you're having problems with rodents, or you want to save some money. Fiberglass might then be appropriate there. Fiberglass is also good for fiber to the home round drop cables. And FRP rod you should use when rodents are a known problem, as long as spans are short to medium. But you got to check the details on that before you would select such a cable. In addition, if squirrels are a real problem, we can add an additive to that outer jacket, and you can increase that rodent resistance rating up to an A+. And FRP rod does have another use, and it's excellent if you're trying to make flat drop cables for a fiber to the home type project. So most of the time, stick with ARAMID, but again, if you're special situation, talk to us and we'll help you decide if maybe fiberglass or FRP rod might be appropriate for what you're trying to do. Next up, core design. There are 2 choices, back to 2 choices, dry versus flooded, also called a wet core. In the issue with this is in the core, between the tubes, and you also use, like in this cable, there's a place for 6 elements around the center strength member. And maybe somebody wanted a 48 fiber cable. So you would have 4 tubes and then 2 filler rods. These are usually made of plastic, like the low density polyethylene, or could be something else as well. Some suppliers outside the United States will even use empty tubes. So they'll just fill a tube, no fibers, and put that in as a placeholder here. But regardless, you end up with these little voids between the tubes called interstices. What do you do with them? Well, traditionally, what you would do, the original design was to fill them with gel. And the gel is good. It does the job well. It keeps water 100% out of the core, right? Because if this is filled and the jacket gets breached, the gel is there to stop the water from even getting into this area. It also gel's cheap, 5 to 10% cheaper compared to doing a dry core. But the disadvantages are that it's messy for the splice prep. We will compare and contrast that with dry tubes in a moment. But when you're doing the splice prep for an ADSS cable, you're probably trying to prep about 6 feet, roughly 2 meters of tube, maybe a little bit more, maybe a little bit less. So you've removed around 6 feet or 2 meters of this ARAMID and the outer jacket. If there's an inner jacket, you took that off too. And now you've got all this gel just sort of oozing everywhere. So it is a mess, no doubt about it. And because it was a mess, dry cores came about. And what they do is they use water swellable yarns or tapes sometimes in these interstices. You see in this drawing, there's 1, 2, 3 of them, one near the center member and then 2 on the outside. What happens is water gets in and these absorb the water. But the first part of what I said, did you notice? Water gets in and then they absorb it. So the disadvantage is that the water is getting inside the cable core before it gets absorbed. But it greatly reduces the mess of splice prep, and it does lower the unit weight a little. I don't know that that's significant. And these, although newer, they've still been around for 20 years, so they have a track record, a proven track record in the field. So what choice should you make? I'm American, and I think that the dry core is the better overall choice. Not against the flooded core. Again, they are used a lot outside the United States, and technically it is better, but American splice techs hate it, and they will complain bitterly. And if you bought a flooded core cable here in the United States. Next up, tube design. Like I said, we were going to talk about that in a moment, and that moment is now. So you have dry versus flooded. So just like for the core, dry versus flooded. And in the case of a flooded core, it's the tube itself that's filled with gel. And that's what you see in this little picture here. A dry tube will omit the gel and put one of these water swellable yarns in the tube or a powder. There are different ways it's done. The gel is used to fill the buffer tubes in a flooded tube. It's the original design, and it's still the most common around the world. The advantage there is, like in the core, it keeps the water 100% out of the tubes. It's also less expensive. And here's an important thing. The gel in the core didn't really do anything other than block the water. But in a tube, the gel helps the fibers keep their sinusoidal shape. Remember early slide, and I showed the sinusoidal shape of the buffer of the fibers inside the buffer tube? The gel is helping them keep that shape. It also helps the fibers and the tube move together when the tube is changing its elongation, in the case of an ADSS, due to a change in tension. So the fibers stay where they should be, and that's a significant advantage. But the disadvantage of a flooded tube is the perception that it's messy during splice prep. And in this case, I say perceived because I kind of, as you can tell, I disagree with that perception. First of all, when you prep the fiber, you're only prepping 6, 8, I mean, maybe it's a little bit more, but 6 to 8 inches, 15 to 20 centimeters of tube. It's not 6 feet or 2 meters. It's a few inches or a few centimeters. And I submit that it's not really that messy, and that you just wipe it off. It takes 15 seconds roughly We have video on our website of splice prep, and you can actually go look and you can time it yourself. And I have. So I think that that's not really a significant disadvantage, but it's perceived that way. The dry tubes have been around 5 to 10 years or so. I have a question mark here because honestly, I didn't run this down. Somebody might come along and say that, well, it was 11 years and 7 months ago. It doesn't matter. My point is, it's been around long enough that you can't really say that it's unproven. It has a significant field track record. That's the way I would put it. The advantages, it's claimed to be less messy in splice prep, and it's claimed to lower the unit weight. I think the weight savings are trivial, and I think the less messy splice prep is highly debatable. The disadvantages, the water does get inside the tube before it gets absorbed again, just like what happens in the core. And the yarn, or if it's a powder, it doesn't matter. There's nothing to help the fibers keep their sinusoidal shape or move in unison with the tube during changes in elongation. And as a consequence of that, fibers can migrate to the middle of spans, especially in long spans, or they can piston out in the splice enclosures, and it does add a cost. So I mentioned at the beginning, there's some controversial topics in this presentation. This is one of them. I'm really trying hard to do my best to present both sides, but I think you can also tell which side I come down on. When you get to what choice to make, I definitely recommend the traditional flooded or wet tubes. Sometimes, as I write here, tried and true is the better choice. Sometimes, not always, but sometimes. And by the way, we can do dry tubes. However, it's just our technical group's opinion, including my own, that dry tubes should only be used in underground cable or if you're buying a cable to lash. We just think it's a really bad idea, our opinion, for an aerial cable such as ADSS or also OPGW. Okay, next design considerations. How many fibers do you put in a tube? The two most common are 12 and 24. So again, back to the two choices, but there's sort of some others for this particular topic. 12 fibers per tube has been the industry standard for decades, a long time. Everybody knows it. They're used to dealing with it. When you buy splice enclosures, they're good for at least 12 fibers on a splice tray. And it's a good count. Like if you have a project where you're going from point A to point B, but along the way you're making some taps to get to access to a fiber or two or a few, it better facilitates that than using 24 fibers per tubes. But the disadvantage of 12 fibers per tube is that it causes cable diameter and weight to go up as fiber count goes up. It's not really a problem at all until 72 fibers. And even then at 72, or excuse me, at like 96, not a huge deal. But by the time you're getting to 144, it's becoming a problem because at 144, you have to use 12 tubes. So you got to find a place to put them all. And above 144, this becomes a big problem. Obviously, the more tubes, the more cost. So all else being equal, you could save, depending upon the fiber count, 10% or as much as 50% if you're using 24 fiber tubes instead of 12. And obviously, the more tubes you have in a cable, the more time you need for splice prep. 24 fibers per tube is newer, but again, kind of on the order of maybe 5-10 years kind of thing. You see them. And you decrease cable diameter and weight, especially at high fiber counts. You save money. You reduce time for splice prep. And it works great with most standard splice trays. Most can accommodate up to 24, and there are a lot that do more than that. And even some fiber splice trays that are nominally 12, you can make 24 work. Not all, but some. It is newer, so you do have to check to make sure that your splice trays can hold the 24 fibers. And the disadvantage, not as conducive to taps as if you're using 12 fibers per tube. Now, I mentioned there are other counts, and just as one example, a 48 fiber could be 4 by 12 or 2 by 24, but it could also be 3 tubes of 16, 6 tubes of 8, 8 tubes of 6, or even 12 tubes of 4. So less than 48 fibers in a cable, 8 or 6 could reduce the overall cable diameter. It depends what else you're trying to achieve in the cable design. And counts such as 6 by 8 and 8 by 6 do facilitate taps and mid-span access, which is basically a variation of a tap. And that could be really helpful if you're doing a fiber to the home project. But disadvantages, it wouldn't be the norm. So, people would have to kind of, think about it, especially when it came to splice prep. You are increasing the cost. And at anything above 48 fibers, you're definitely increasing overall cable diameter and weight. So what choice to make? Well, again, another example of a situation or a design aspect that really depends upon what you're trying to do in your project. There's not a wrong answer here. Okay, moving on. So this is my second controversial topic, tube material, because there are two that are used and most suppliers can only do one or the other for practical reasons. The first up is polybutylene terephthalate. Peter Piper picked a peck of polybutylene terephthalate. Try saying that 3 times fast. PBT is the way it's commonly known because it's a lot easier to say. PBT. Advantages. It's got high crush resistance. In a cable, it's going to be about 60% greater than a cable that was made using polypropylene, which I can say a lot easier. Polypropylene, or PP, is what I call it here. So high crush resistance and durability, and these properties make sure that your cable works well with dead ends. So the hardware supplier won't have a hard time holding that cable up in the air. Why? Because the cable, it's more like sturdy or stout. You really grip onto it well. It has high tensile strength and it has excellent temperature resistance. But disadvantages are it's more susceptible to being kinked during splice prep, and this is a significant disadvantage. Splice techs do have to be reasonably cautious and careful when they're handling the tube, because otherwise they can kink it and that could do something bad to the fiber. And it is more expensive. Polypropylene is very flexible, and so tubes are much less likely to kink during splice prep. And splice techs do like this a lot. And it's also less expensive, but it has some significant disadvantage. It has much lower crush resistance and tensile strength, as I mentioned up above, and it's not as durable as PBT, and it has much lower temperature resistance, especially at lower temperatures within the range of which an ADSS would be expected to operate. So I think it's effectively reducing overall long-term reliability. And as you can see, and on behalf of InCab, we think that PBT is the way to go, just the best overall choice. But obviously some of our competitors would disagree with us on that. draw your own conclusions. Oops. Yeah. Okay. So we've discussed the 7 design aspects of ADSS, and now we're moving on to the topic of how you make the tubes and how you make the core itself. And I said that those would be important, and here's why that is. So the tubes, when you're manufacturing the tube itself, your supplier should have continuous inline excess fiber length, right? So what that means is that sinusoidal shape that we talked about many slides ago. This is just a fancy way of saying that you want the fibers to have a consistent sinusoidal shape, the way you designed it to be, and each and every fiber having exactly that same shape in that tube. So to do that, your production equipment needs to be monitoring that and controlling that 100% of the time during the process. World-class cable manufacturers can do this. You just have to verify that they're in fact world-class and that they're doing that. The optical core, which I showed you in previous sketches, the core itself needs to be stranded using a conservative lay length. So remember that picture I said where I showed you how a tube gets stranded around a cable? Well, I can make that stranding pitch either really long or really short. If I make that pitch really long, I think I need to go back and show that. Pardon me for a moment. So if I make this distance really long, I, as a cable supplier, that's great, right? Each revolution of my machine makes more optical core. So productivity goes up, profits soar. That's great, but performance suffers. So you, as a user, you actually want this lay length to be short. And maybe you want it to be like a spring. Of course, turns out there are actually technical reasons you don't want it to be too short. And so we end up with a compromise. So you need to use a good lay length that balances the or factors in the performance aspects of the optical fibers. And the core should be stranded using reverse oscillating lay. And ROL is when the lay direction reverses every few inches. So you start stranding the tube in, say, a right-hand direction, and then after a few inches, you switch to left hand, and then after a few inches, you go back to right hand. And the reason you do that is that it makes splice prep easier. And if you end up doing mid-span access, which is a version of doing taps that I talked about earlier, it facilitates doing that. It just makes it really easy and fast to get the tubes out so you can start working with them. These aspects work together to maximize the zero fiber strain margin. We talked about that on the same slide I went back to before. So the fibers, ideally, we'll talk about this in a minute again, you don't want the fibers to be under tension under everyday type conditions. Now, sometimes you have ice and wind loading on a cable, and the fibers will experience tension up to the maximum rated design tension of the cable. And at that point, they're experiencing some tension, but you want to minimize it. So these elements help you maximize that zero fiber strain margin and minimize that fiber strain or fiber tension at that maximum rated design tension. So that lets us move on to other important design considerations. What about those sag and tension characteristics? And when do I need a tracking resistant jacket? Sag and tension, this is just a primer only. I will later do a detailed presentation just on doing sag and tension calculations. ADSS is different than OPGW or other metal cables. In metal cables, strength is being used to control sag. With ADSS, you're principally using the strength to control that fiber strain. However, Because it's a plastic material, it's kind of stretchy, right? Like a plastic material you would expect it to be compared to a metal material. And as a consequence of that, horizontal blowout during wind loading, wind or combined wind and ice loading, can be significant, and you do have to check that. So when a cable sags, it has a vertical component, which is what you can see here. But when there's wind blowing on it, there's also a horizontal component, and you need to check that. The vertical sag under ice loads with ADSS can cause the cable to exceed ground clearance limits, and so you have to check that as well. Now, cable suppliers, I said strength is required to control the fiber strain, and cable suppliers have a design policy on fiber strain. They may kind of hold that close to their chest, but I'm telling you, they've got one. We have a good one, and I'm okay with sharing it. So in our case, we want zero fiber strain at what I would call an everyday tension. So unloaded, no ice, no wind. And we want limited fiber strain at the maximum loaded tension, so that maximum rated design tension level. Ideally, we try to keep the strain less than 0.2%. Remember, that's that ideal limit that I said came from Corning research. We think it's acceptable to go up to 0.3%. Yes, you're taking more risk, but we think it's an acceptable risk, that probability of failure is still mighty low. And then it's risky to go above this and get up to 0.4%. We don't like to do this. Like, I would try to do everything I could to avoid that. And if I was doing this, I would tell you it. And I would also cut our standard warranty, probably, being brutally honest and candid here. And anything above that, we just think is crazy. So this would be like absolute maximum. You had to twist my arm to get me to agree to it, kind of thing. And then with sag and tension, with ADSS, the industry convention is to have the sag be between 1 and 1.5% of span length at every day. So this nominal unloaded condition. No ice or wind loading. Don't really know exactly how that came to be, but it's just been a industry practice for a long time. Before I even began working with ADSS. And then I prepared this slide, and lo and behold, last week I saw one of my competitors gave a customer a sag chart that was based on 0.75%. So, like, what do I know? First time I'd ever seen that. Don't know why they did that. I already thought 1% was really tight. Most metal cables on an everyday condition will sag around 2 or 3% of span length, so that really surprised me. Most of the time, this is what I've seen. So where do you get the actual data that you need from? Well, you got two choices. Manufacturers provide charts. I just referenced one that my competitor did, and we do that too. And this is probably the most common way that ADSS sag and tension is done. And it's in big contrast to how most utilities do it with metal cables. Most utilities want the sag characteristics usually expressed in the form of a polynomial chart, and they do their own sag calculations from it, and they include a lot of different loading conditions and whatnot. Whereas these manufacturer provided charts are pretty simple. They usually just give an everyday condition, and they give the sag vertical and horizontal at whatever the loading, the appropriate NESC loading condition is. So they're really kind of simple. And that's why I say here, you need to check and make sure that it's covering your loading criteria. Because sometimes, you're doing things beyond just what the NESC loading district says. In any event, your second choice is that you can generate your own data. Powerline Systems PLS CAD or Southwire SAG10. PLS CAD, you obviously need to get a wire file, and you can get that from the cable manufacturer, or they have a library of some cables on their website. The Southwire program is not really good for all cable manufacturers. It's really written around one particular cable manufacturer, and that's seems to be about all it can do. And then just a comment, ADSS SAG charts are not temperature related. Remember, if you go back and think about what your strength element was, ARAMID and fiberglass don't change a lot with temperature. Fiberglass does more than ARAMID, but still compared to metal wires, a lot less, like more than an order of magnitude less. So generally, you don't worry about the temperature, which is perhaps one reason why many utilities have been able to work with just these simple manufacturer-provided charts. And then, like I say, we will do a separate presentation to talk about all of this stuff in great detail, and specifically how you would generate your own data. That's going to be the main focus of that presentation. Now, sometimes customers will say to me that someone, another cable manufacturer, specifically told them that snow and ice don't accumulate on ADSS. And this is like the best picture that I could find to illustrate that that ain't so. In this particular picture, what you see here, this is an ADSS cable, and it's got quite a lot of snow and ice on it. In contrast, this also appears to be a second ADSS cable on the same line, and it doesn't have any on it. But this one's got a lot, and the phase conductors don't have any on that. So this is basically a myth. What some have said is that, well, it's plastic cable, so it acts like an old-fashioned ice cube tray. You've seen those plastic ice cube trays, and you know how you would sort of twist them to pop the ice cubes out. And so what they were saying was somehow the plastic was helping to shed the ice. And maybe there's some truth to that, but it's not the whole truth, because this picture shows that. And by the way, some utilities have had problems when there's been a significant elevation difference from one pole to another of ice breaking off in chunks. Like you see this one here, there's sort of a gap here and a gap here. And the ice had, in some cases, is broken down span. And one of these chunks breaks off and goes sliding down the cable and crashes into the dead end. And that's actually caused damage to hardware. So ice and snow definitely do accumulate on ADSS in at least some conditions, and therefore you do have to check for it. If somebody tells you that it doesn't, show them this picture and then call security. That's what I would do. Now, electrical issues. Standard polyethylene jackets, whether they're medium density polyethylene or high density polyethylene, they're limited to 12 kV space potential or less. Now, some of you may be thinking, I am an electrical engineer, and some of you are also electrical engineers, and you'll say, Mike, it really should be an electric field, which would be kV per unit distance, like kV per inches or kV per meter or whatever. And you're right. But this is the conventional way that it's talked about in the industry, and it works. Again, it would be more precise to talk about it in terms of an electric field, but as a practical matter, like I say, this works. Polyethylene, whatever it is, degrades in a strong electric field, and you'll get tracking, and tracking will lead to the jacket burning through. You get a hole in the jacket, and then you get water inside. I mean, basically just bad things happen. The burning can continue, and it can burn whatever the strength element is, and then the cable can just fail mechanically. So, or the water can cause optical failure. So nothing good happens, bad things happen. So therefore, if the space potential goes above 12 kV, you need a tracking resistant jacket. You also will need corona coils, because when the space potential gets that high, you're going to end up with corona, which is like an electric discharge at the tips of the accessory rods, and that's going to damage the jacket. So corona coils, what they do is they grade out that electric field and thereby eliminate the corona. You could also have some induction issues on your pulling line during installation if you're installing a tracking resistant ADSS on a high voltage transmission line live. So you have to be careful about that too. And even when you're using a track resistant jacket, the maximum that you can get to is 25 kV. And here's some pictures. This is that corona problem that I mentioned. And corona coils are the solution. Now, I need to take that information and make it more practical for you. So generally speaking, up to 35 kV, there's not a danger of tracking. You can use just a standard polyethylene jacket, no problem. From 35 kV to 138 kV, you're also likely no danger. You've got to really work hard almost to make a problem. And I'll show you that in a minute in detail. And if there's any concern, even the remotest possibility of a concern at say a 115 or a 138 kV or something in between, just ask the supplier. They can help you check that. Above 138 kV, you get into the could be a danger. You know, so in the United States, like there's a little bit of 161 kV, so you got to be careful. And again, the supplier can help you check it. And at 230 kV and above, absolutely, you know, you have to use a tracking resistant jacket. So by the time you're at 230 kV, definitely, and you've got to use the corona coils on it. And a supplier can help you verify this. I mean, maybe you got a 230 kV and some unusual situation where you're planning to put it isn't going to be a problem. But you know, again, I would want that verified if I were in that situation. To do that, a cable supplier can get some information on the geometry of your structures, and they can do some calculations and print out a equipotential chart like what you see here. So what you see here, the white is less than, for whatever reason, I did this one at 12.5 kV. The green is 12.5 to 25, and any other pretty color is basically death to an ADSS cable. So a standard cable could be used in the white. A tracking resistant cable could be used in the green. And by the way, if you're using a line, you know, and you got an H frame, or kind of, this is kind of sort of an H frame. But the structure geometry changes somewhere, like at an angle, for example. You got to analyze that separately. So you know, you need to do it by structure type, not just you know, check a tangent structure like this one and assume it's okay everywhere else. And in fact, some would argue too that at an angle structure, you might have to do this as some kind of three-dimensional analysis. And I wouldn't disagree with that point. So how would you use a chart like this? Well, you can kind of take a hint from what I said a moment ago. If the white is 12.5 kV, well, you could attach to the white as long as this gives you, this says 25 feet roughly, as long as this means that you have enough ground clearance, yeah, okay, that would be fine. But probably not. And so if you're trying to then get it higher on the structure, as long as you stay in the green, you're okay. You're just looking for a convenient place where you can attach the accessories, whether it's a dead end or a suspension clamp. And like I just said, you also need to check for adequate ground clearance. I mentioned that on a 138 kV line, you have to work hard to make a problem. Here's an example that I did for a 138 kV structure. And you can see you're getting pretty close to the phase conductors before you begin to have a problem, about 6 feet away, which is about what, in this case, which is about what you would expect, to have to keep clearance for anything else from the 138. So, here you could attach, or on the back side of the structure, no problem. But somebody might get clever and say, well, here, I'm going to put it at the top of the structure. Well, you can see there's a little bit of green there. So, it could be a little bit risky, but then maybe you could put a bayonet on here and get a little bit of separation just to make sure you don't have a problem. So you get different options, but you have to get you have to try hard at 138 kV to not be able to use a standard jacket. And I almost forgot to mention ripcords. Splice techs like ripcords. A ripcord is just a really strong, like a yarn that's used to tear through the jacket. So they'll grip onto it with a pair of pliers or a screwdriver. They might wrap it around a screwdriver or something and use it to pull through the jacket. And there are splice techs that love it. I think a good jacket stripping tool like what you see here is at least as fast and easy as using a ripcord, but some splice techs love it, and I'm sure they'd say I'm totally wrong. And so it's a detail that you, if you're working on a project, need to manage. At InCab, what we do is we put one ripcord under each jacket. So if it's a single jacket design, you will get one ripcord on that outer jacket. If it's a double jacket design, you'll get two, one under the inner and a second one under the outer. Some customers, though, want two under every jacket, and some suppliers don't use any unless you ask. So again, it's a detail that you need to pay attention to get the supplier to do what you decide you want. Okay, and in closing, we also offer our advanced cable engineering system, ACES as we call it. We have an ADSS version and an OPGW version, and the ADSS version can help you select the optimal cable and generate the bill of materials for the cable and the accessories, and do real lengths and plan logistics, and even estimate a cost. And it's really helpful, and I hope that you will check it out. You can find it on our website, or you can go to this link. And that concludes today's presentation. And so now I will open it up for questions. Give me a moment here. I have to do this and find the Q&A session. One question I see here is, if span lengths are shorter, say 300 feet or less, is single jacket as reliable as a double jacket? And my colleague Dan said double jacket is more reliable. The added cushion and mechanical protection is just better. And I agree with Dan. If I reframe that question a little bit as, is single jacket good enough? Then I would say, yeah. For a 300-foot span, I think it's okay. Now, but again, remember, fiber count is an issue. So if you were doing a 288 fiber cable, and we got a customer doing that, it's going to be a double jacket design. But like at 24, 48, something like that, I think that single jacket is reliable in the context of good enough. But if you frame the question as, is single jacket as reliable as double jacket, the answer is no. And does both of the jackets have the same tracking characteristics? Talking about the double jacket cable, obviously. Yes. I mean, the polyethylene is the polyethylene, and you're going to get the same performance. If you're making a track resistant cable, though, you only need the tracking resistant material on the outside of the cable. The way the tracking mechanism actually works is such that it doesn't get to the inner jacket. Let's see, next question. When is HDPE the best choice? That's a good question. That is really more a matter of personal preference. The cracking problem, there are HDPE cables that have been in the field and have worked reliably for years. The cracking problem comes up in like when the temperature goes to like -30, -40 C. And even then it doesn't always happen because of just the way things are in the field condition. I can't really think of a reason where I would have to use HDPE or where I would use HDPE. I'm sorry if that seems like a weak answer, but it's like if you think that's good and you want it, then you just need to put it in your specification. I think that boils down to more of a personal preference thing than any hard technical reason why to use HDPE versus MDPE. Question, can you mix dry core with flooded tube? And I see Dan has answered. And yeah, in the United States, that's been the most common construction, is a dry core with a wet tube. The person also asked about the reverse. Could you have a wet tube with a wet core with a dry tube? I suppose in theory, but I've never actually seen it. And honestly, I don't know why you would do that. Usually if you want dry, you want everything dry. Oh, Dan wrote that already too. Do space potential issues only apply to ADSS or to any polyethylene jacketed cable? Well, they would apply to any other cable as well, but the practical reality is you don't see lashed cable used on 230 kV transmission lines. And even then, the messenger cable would effectively ground out the field at that point. And I'd have to do the calculations to verify what I'm about to say, but I think what you would find is when you did the calculations, that the lash cable would end up being in a lower space potential and therefore not subject to tracking. However, lash cables, especially on high voltage lines, remember I talked about the #1 killer of ADSS in the field was shotgun damage. And so some people have tried to get clever and used a lashed armored cable, so a corrugated steel armored cable on a transmission line. And then they thought, well, at the splice points, we'll just ground it. And it doesn't work that way. An electrical engineer will understand what's wrong with that thinking, but the ground doesn't actually make the voltage go literally to zero. And so at least one utility actually did that and had a couple of its splice techs get injured during the splicing process because they thought you just had to ground it and then you're done. And no, it doesn't work that way. So let's see. How would you avoid wet tube to space potential? Okay, next question. How would you avoid this issue when cables are close in underground systems? Well, okay, today is really supposed to be talking about ADSS, but I will answer the question. You have the same problem. So if it's an underground circuit and you put a corrugated steel armored cable in it, you're going to have, in that case, you're going to have significant induced voltage and current on the armor. And of course, in theory, you can just ground it. In practice, there's more to it than that. And for that reason, the more common solution is to put just a plain black jacket cable, a duct type cable without armoring in a conduit in proximity to an underground circuit. The other solution that you could do is what I showed you before, that a fiberglass plastic rod, fiberglass reinforced plastic rod armored cable, that could be direct buried. And if you had a reason to suspect or be concerned about something happening, you could even do a little bit of belt and suspenders by taking an armored cable, a dielectric armored cable like that, and putting it in a conduit and putting it underground. So basically, the way you avoid electrical issues in underground circuits is get rid of the metal. When an ADSS cable is clamped at a dead end, is there any chance that HDPE jacket got elongated due to tension? Well, yeah, and that's true. HDPE, medium density polyethylene, that's something that the hardware supplier factors into their dead end design. And that's why most dead ends are the formed wire type dead end, and they tend to be long, because what you're trying to do is couple the tension that's in the cable to the structure, and you're doing that through the dead end body. And by making the rods long, you make that transition smooth and easy through the jacket. You distribute that transition of tension over a greater distance, and that helps you prevent the jacket from tearing. And so to go back to the person who asked about using HDPE, well, HDPE in theory would be better for the dead end design again. But as a practical matter, I think the hardware suppliers design their stuff around the range of cables that are out there. And so the people using polypropylene and using medium density, they sort of factor that into their design. And so you don't really get any net benefit from using, say, an HDPE cable with PVT tubes with the dead ends holding, but you could say that, well, you're getting a little bit more of a margin for error there. But that's kind of highly theoretical. So, what cable design parameters would be adjusted to control cable sag under ice and wind? How would those parameters adjustments impact cable cost? Oh, well, the simple thing that you do is you add more strength member. So if it's ARAMID, add more of it. You increase the cable rated breaking strength until you get what you need. And of course, the more material that you put in, you're driving up the diameter and you're driving up the cable cost with it. So that's the effect. I mean, I can't. I would have to know the details in order to quantify it for you. How much that would increase the cable diameter and how much that would increase the cost. Okay. So I don't see any other questions. Anything else? Okay. Nothing's coming up. We're at 12:24. Oh, wait, here we go. Something came up. If a wedge dead end clamp is used in network, then how one can avoid elongation of jacket due to tension? It is a common issue with dead end clamp and ADSS cables. For ADSS cables, I am not a fan of wedge dead ends. My experience, I know of a number of cases of jackets ripping with wedge dead ends, and in recent memory, I can't think of any that happened with the formed wire dead ends. It's kind of beyond the scope of today's discussion, to go into elaborate detail about this, but the problem with the wedge dead end fundamentally, though, is that remember I talked about you have to couple the tension in the cable to the structure, and you're doing that through this mechanism called the dead end. With a formed wire dead end, you're doing that over the entire length of the rods. Now, the dead end suppliers will say, no, it's really the first, I don't know, 2/3 of them or whatever. And the rest is kind of margin for error or for other purposes. But still, the point remains. You're doing it over a great distance. So if you were to calculate it on some basis, maybe pounds per inch, it would be, pounds per inch over a great area, a great length. And so that number gets low. With a wedge dead end, you're doing it over a much shorter distance. So that transitional pounds per inch value has to go up. I mean, it's just the physics. And that means there's more stress on the jacket, regardless of what type of material is. And so I don't think that's a good design concept from the very beginning. And that's before I also would point out that there are some production practical matters with the tolerances when a manufacturer goes to make something. And I think those don't go favorably for the wedge type dead ends. So in my opinion, I don't like wedge dead ends. I think sometimes they might be appropriate on very short spans, and maybe in locations where you don't expect there to be heavy ice or wind loadings. But by the time I've put that many conditions on it, it's like, what's the real benefit of them? The formed wire dead ends, under that situation, you could use a limited tension formed wire dead end. It's not going to be that long, which means it's not going to be adding a lot of time or cost for the installation of the dead end. So what's the real net benefit under that condition? So I still, I come at it from a different perspective, and I still end up in the same place. I'm just not a fan of wedge dead ends for ADSS cables. Hope that answered your question. So anything else? Kind of last call? Okay. If you think of something afterwards, feel free to drop me an email, mike.riddle@incapamerica.com. We'll keep going here for a minute because I needed, you see here on this last slide, if you want a copy of this presentation, send us an email at webinar@incapamerica.com. And so my email address is mike.riddle@incapamerica.com, and that'll get to me. And we will, I'm glad to help you with anything. And I got to go back. If you wanted the professional development credit hours for this course, you need to take the test. And I don't, send us the request. I guess that information will go out later. Natasha, if you're on, can you help me out on this? Are you going to send everybody an email and give them the link for the test? Yes, that's what you're going to do. Now I know it. And then secondly, you'll get an email with a link to take the test. My philosophy on test is not to ask questions like, what was the third bullet point on slide number 5? Kind of thing. My philosophy on testing is that it should reinforce what you learned and therefore contribute to the overall learning process. So it's not a hard test. If you paid attention, you'll do fine on it. You can get the credit hours. There will also be a link to a survey. So we would appreciate your feedback about this presentation, and maybe you have ideas for other things. Look for that email and please give us some feedback. And if you'd like to get the credit, please take the test. And with that, I want to thank everybody for your time and attention and participation in today's webinar. Keep an eye on your email box, and we'll do another one in another month or so on another topic. And that's all I've got. Thank you. Take care. Stay safe. Bye-bye.